Cool. Well, thanks for having me. So I'm going to talk about some joint work with Matt Yancey, and we'll just start out with sort of how do you measure the sparsity of a graph? And there's different ways to do this. One that's kind of common is this notion of maximum average degree. So for a graph H, the average degree is twice the number of edges over the number of vertices. And then the max average degree just says that you take the maximum over of all subgraphs in your graph G. So sort of some simple examples. Having mad less than 1 just means that you're edgeless, because as soon as you have an edge, then that edge and its endpoints would give you a subgraph with with average degree equal to 1. So here's a graph that's mad less than 1. Having mad less than 2 is being equivalent to being a forest. So as soon as you have a cycle, then that would have average degree 2. And so here's an example of a graph with mad less than 2. One thing to point out about this is you can get arbitrarily close to a mad equal to 2 with forests. So, so that is a strict inequality, and you can sort of get very close to it holding with equality. An example, when you go to mad less than 4, is planar bipartite graphs. And so this is no longer if and only if, this is just one nice example. And one thing to notice is if you just take big grids, then again, this approaches average degree equal to 4, because sort of everything on the inside has average degree equal to 4. And then there's a little bit on the outside, but this boundary, the fraction that's on the boundary is going to 0 as your grid gets big. So you're approaching 4 from below. For mad less than 6, planar graphs are sort of the standard example. And again, you can get arbitrarily close to 6 by taking a big 6 regular grid, except it's not 6 regular just on the boundary. And again, the fraction of the vertices on the boundary is going to 0. So you get arbitrarily close to 6. And these are really all just special examples of this statement here, that if you have girth, which is your shortest cycle, if the shortest cycle has length at least some value g, then your mad is strictly less than 2g over g minus 2. And that's an easy exercise just from Euler's formula. And again, this can hold with near equality as well, if you just make a big grid of sort of faces of length g. And it's really easy to see this when g is even, and it's sort of slightly harder when g is odd. But everything in the inside has average degree g, and then the stuff on the outside has degree slightly less. So, so that's the notion of sparseness that we're going to talk about, or sparsity. And now we're going to talk about coloring. So we typically think of standard vertex coloring as partitioning into independent sets. If you want to rephrase it in this language of max average degree, one way to say that is that each of these sets that you're partitioning into has mad less than 1, because we saw that mad less than 1 is the same thing as being edgeless. So the question that we're looking at is, what if we want to k-color a graph, but we're not allowed as many colors as the chromatic number? So now you're going to require that you're going to be forced to have some edges that will be monochromatic. But what can you get? So every talk on graph theory should have the Peterson graph somewhere. So here it is. The Peterson graph has chromatic number 3. So what if we're only allowed to use 2 colors? Well, you can't now require that each of these sets of vertices is going to be independent, but maybe you can require sort of something in that direction. And so, what if you don't require that the max average degree is less than 1, but so here, for example, if you require that it's less than 4/3, so 4/3 is the average degree of a path on 3 vertices. And so if you're strictly less than 4/3, then that means you don't have any path on 3 vertices. So it means that each component is either an isolated vertex or an edge. And so Hendry, Norn, and Wood asked this question about basically you're trying to partition the vertex set of a graph G into 2 sets A and B, where each of them induces a subgraph with low MAD. And so the idea is if you're given the bounds that you want for MAD of the induced subgraphs, how big of a MAD can you allow for the input graph so that you're always guaranteed such a partition? So in this instance here, well, let me just do one more. So they said, particularly they asked about G1B, right? And here, if you're requiring that A has MAD less than 1, then you're requiring that A is an independent set. Okay, so so here our independent set is these guys, and in this case, now we're able to get GB down to, so this is the max average degree of this black subgraph is 1. And so anything that's strictly larger than 1, this would work as a valid partition. Now, when B is less than 2, what this really amounts to is you're partitioning into an independent set and some forest. And the order that you're allowed for your trees in the forest is directly a function of this B. And you can just work through the algebra, and it turns out that a tree on K vertices has max average degree 2 minus 2 over K. So rather than muddle through this algebra every time, we're just going to think about things in terms of partitioning into an independent set and a forest where each component has order at most K. So does that problem make sense? Any questions? So I should say, as we're going along, if you have questions, feel free to just turn on your mic and ask a question. That's totally fine with me. If you want to do it in the chat, I won't monitor the chat, but probably Peter or Rose will, and you can pass them along if they're relevant. Okay, so let me tell you what we proved. So what we said was we found this threshold, which turns out to be this 3 minus 3 over 3K minus 1 and 3 minus 3 over 3K minus 2. And this is a threshold where if your MAD is less than that, then you have an IFK coloring. So this is, you partition into 2 sets where one is an independent set I, and the other one induces a forest where each tree has order at most K. So here's an example, just to make this very concrete. So this graph has average degree and max average degree 3 minus 1/5. So if you write that in this language, then you would say 3 minus 3 over 15. And 3 minus 3 over 15, if you plug in K equals 5, then that's down here. That's 3 minus 3 over 13. And that threshold is too low. So this doesn't guarantee you an IF5 coloring. But if you plug in K equals 6, 3 minus 3 over 17, it does guarantee you an IF6 coloring. So here is an IF6 coloring. So you've got this one tree here of order 6, and you've got some other trees up there of order 2, and then the white vertices are an independent set. So this was our result, and in fact, this is sharp infinitely often for each K. And so I'll show you the sharpness examples in a little bit. Before I do that, let me just mention a few corollaries. If G is planar with girth at least, so there's results for girth at least 9, girth at least 8, girth at least 7. And it sort of makes sense that as your girth is going down, the number of vertices that you have to allow in your forest is going up, right? Because you can have it's a more dense graph. And so you're gonna have to put more of those edges into the forest is sort of the intuition. And the proof is really straightforward. So for this first result with girth 9 and components of order at most 3, all you do is you just plug 9 into that result that I showed you on the first slide, where it says, if you have a planar graph with girth at least 9, then its MAD is strictly less than 2 times 9 over 9 minus 2, which turns out to be exactly 18/7. And then you plug in 3 up here, and you get 3 minus 3 over 7, which is actually 18/7 as well. And then it's a similar thing for 4 and for 6. Turns out in those cases, you don't get a match. It's this is sort of strictly less than, or sorry, strictly greater than what you get from girth 8, and this is strictly greater than what you get from girth 7. But one other comment is that this proof about the sharpness, which I'll show you in a minute. Well, actually, right, the proof for the sharpness doesn't require that our components be acyclic. So even if we relax that condition and we allow our components to have cycles, but we still put the bound on the order, then those thresholds are still sharp. And we'll see that coming out of the proof of sharpness in a minute. So before I get to that, let me say a little bit about previous work on this. So this is a nice result of 2 PhD students, I believe, that just showed up on the archive in fall of, I think it was fall of 19. And I don't think it's published yet, but what they say is, if you want to drop the max average degree as much as you can, there's always an independent set I that will drop it by at least 1. And this criteria of having an edge is sort of silly, because if you don't have an edge, then your MAD is 0, and so you can't drop it at all. And so here you can think, in this example of the Peterson graph, if you delete this independent set, you drop the max average degree from 3 all the way down to 1. So this is, Peterson graph is particularly easy for this sort of partition. And similarly, they said, if you want to drop it by 2, you can always do so by deleting some induced forest. And so again here, if you were to just delete these black vertices, that's a forest, it drops the MAD from 3 all the way down to 0. So again, this is particularly easy to do for the Peterson graph. But so this is a nice, nice paper. It's fairly short. It uses some techniques from max flow min cut. So I won't say anything more about that, because it's really a different approach than what we took. And this is just sort of rephrasing their results in this language of the question of Henry, Norton, and Wood. So this statement here is saying, if you want to 2-color the graph, and what is 4/3? We said 4/3 is the average degree in a path on 3 vertices. So if you want the MAD strictly less than that, then what it's saying is, in each color, you're allowed to have components of order at most 2. You're not allowed to have any component of order 3 or more. And so they said, if that's the kind of coloring you want, then the threshold is 14/5. And they gave a proof of that, and they found sharpness examples, infinitely many sharpness examples. This one here is, again, you've got 2 colors, and the first color class has to be an independent set, and the second one, each component can have order at most 2. So this is an independent set and a matching. And they said MAD of 12/5 or less is fine, and there are infinitely many sharpness examples for that. And this actually is the case K equals 2 in our main theorem. And so it was in some ways motivated by this earlier paper. And then there's a bunch of other results that I won't get into a ton, but in each case, these have stronger hypotheses than what we had, and they get a weaker conclusion. So these are all subsumed by our main theorem. Okay, so rather than just talking about coloring, we're going to talk about critical graphs. And a critical graph is one that doesn't have the partition that we want, but every proper subgraph does. And so what we'll do is we'll sort of try to get some necessary conditions for a graph to be critical. And then we'll say, if you have this bound on MAD, then none of your subgraphs can satisfy that condition to be critical. And so if you don't have any critical subgraph, then you're going to have one of these colorings, kind of akin to standard vertex coloring. Okay, so here's the sharpness example. And let me talk to you about what the different parts mean. Anytime you see something in green in this picture, it's a multiplicity. So this K/2 floor, what this is these are called two threads. So it's a path of length 3 where the two internal vertices have degree 2. And this green is saying there's K/2 of those two threads that share these same endpoints here, but they have distinct internal vertices of degree 2. And then similarly for this pendant triangles. So again, this multiplicity, you have a bunch of pendant triangles. They're all pendant at this common vertex here, but the other degree 2 vertices are distinct for each of those pendant triangles. So the idea is first we're going to show that this graph doesn't have this coloring that we want, this IFK partition. And the way we'll do that is we'll assume that it does, and we'll sort of start at this left end here and work down, and we'll make it almost all the way down to the end, and then we'll fail at the very end. So let's give names to these vertices. We'll call this V0, W0, and X0, and then V1, W1, X1, and so on going down. And the first thing to note is that on this triangle, at most one of those vertices can be colored I. And what I want to show you is that you can't color V0 with I. It's going to have to be colored F. And the reason is, suppose that you colored it I, then each of W0 and X0 would be colored F, sorry. And from each of these pendant triangles, each of them would get another neighbor that's colored F, right? Because in the pendant triangle, you can have at most one of those two neighbors is colored I because it's a clique. And so if you had that, you've got K-1/2 F neighbors here for W0, and then you've got K/2 floor, which is the same as K-1/2 ceiling, F neighbors up here. And so together, the F neighbors from X0 and W0, that makes K-1 F neighbors when you add those. And then you add in 1 for X0 and 1 for W0, and you go from K-1 up to K+1, which is too many vertices in your F component. So that's not allowed. So what it means is one of those two has to be colored I, and then that means that V0 is going to be colored F. Now, you can repeat the same argument down here, and you won't quite get a contradiction, but what you'll see is, you'll see that this guy's got to be colored F, V0's got to be colored F, and he's going to be in a component of order exactly K, an F component of order K, because he's either getting F neighbors from W0 or from X0, and together they have sort of all of the vertices you can have in an F component. And so this guy, V0, will be in an F component of order K in any good coloring. And so now what that means then is if he can't have any more F neighbors than what he's getting from this triangle, then it means that all of these here off to the right are going to have to be colored I. And since they're colored I, then these batch here are going to be colored F. And now we're going to play the exact same game down here with V1, W1, and X1. And these batch here that are colored F are going to play the exact same role that the pendant triangles played on the first triangle. And so you can repeat this argument all the way down. You'll get that V1 will be in an F component of order K. So these guys are colored I. So then these guys have to all be colored F, and then the same for V2, all the way down to the end to VS. So you're almost there. We've almost made it to the end and everything works, but now we're stuck because we've got this last pendant triangle. And this pendant triangle is gonna give us at least one more F neighbor, but we don't have any more room for an F neighbor in this F component. And so you'll end up with one component that's too big. And so that's the proof that you don't have this IFK coloring. And I won't do the proof that every proper subgraph does. It's a little bit of a case analysis, but sort of the intuition is this argument propagated only just barely. And if you take out any edge or you drop any vertex, then there's enough little bit of wiggle room. And then you can get one of these V vertices to be colored in I. And once they're colored in I, then you'll be able to handle this triangle fine at the end. Okay, so that is that's the sharpness example. So this is a family of critical graphs, and you can add as many of these sort of triangle chunks in the middle as you want. What is the average degree of this thing? So the way that we do that is we want to say, when you add another one of these chunks, how many new vertices do you add and how many new edges do you add? And so when you add one of these chunks, the number of vertices you add is given by this. So for each of these threads, you add 2 vertices. So 2 times k over 2 floor plus k minus 1 over 2 plus k minus 2 over 2. And then you add these 3 more vertices for the triangle at the end. Okay. And if you work this out, it is 3k minus 1 or 3k minus 2. And sort of the quick way to think about that is, for a minute, ignore the floors. So if you ignore all the floors, then these 2's cancel with these over 2's, and you just get k plus k minus 1 plus k minus 2 plus 3. And so it works out to 3k. And then when you go back and look at the floors, when k is even, you just lose 1 to the floor here in the middle. And when k is odd, you lose 2 to the floors on each of the ends. So that's the 3k minus 1 over 2, 3k minus 1 and 3k minus 2. Now the other question is, how many edges do you add? So this was vertices. The way to think about edges is to say, for each 2 vertices that you added, you add 3 edges, right? For these 2 threads. The only difference is it's a little bit different for these 3 on the end. So you sort of subtract those off, you multiply by 3 halves, and then you add back for the 3 edges on the triangle that you added. Okay, so that comes out to 3n minus 3 over 2. And now what we really want to know is, what's the average degree, sort of. So what we want is 2m, 2 times the number of edges divided by the number of vertices. What's the change that we get for each one of these chunks? And when you work this out, it is exactly that threshold that I showed you in the previous slide with the main result. Okay. So these things are approaching that threshold from above. And why is it above? So it turns out that this bit on the left has the exact same max average degree as all of these other pieces. The only little bit that's pushing it away from that is this final pendant triangle at the end. You add these 2 vertices and 3 edges. And so it pushes the average degree a little bit towards 3. And so you're just slightly above this. But as soon as you drop even a single edge, then you're back down below this and you're fine. All right. All right, so let me say a little bit about the proof ideas. So we're actually going to prove something about IFK critical graphs. And for the next slide, I'm just going to focus on the case k equals 4, just to kind of try and make things a little bit more concrete. But the idea, we're going to introduce this thing called a potential function. So this is for an IF4 coloring. So what we want to do is we want to understand IF4 critical graphs and show that if you satisfy this bound on max average degree, then none of your subgraphs can be IF4 critical graphs. And so then you'll have this IF4 coloring that you wanted. So these numbers, let me just mention this 15 times number of vertices minus 11 times number of edges. Where are those coming from? If you jump back here, 11 is when you plug in k equal 4, that's this 3k minus 1. That's the 11. And the 15 is this m. So if you plug in here, so what did we say? This is 11, and then you get 3 times 11, which is 33 minus 3, which is 30 divided by 2, which is 15. So this m and this n are directly coming into play here in this definition of our potential function. And so this is just a way of, well, okay, so this is the statement of the theorem. If you're IF4 critical, then your potential is low. And the way to think about this potential being low, being negative, is to say that you have sort of too many edges. And what is too many edges? Well, it's more than average degree 30/11ths. So this is a line of algebra to go from mad less than 30/11ths to row 4 of R greater than 0. But this 30 is 2 times this 15. And why do we need it for all R? Well, that's because it's max average degree. Okay. So what we want to do is, if we can prove this theorem, then it will immediately imply this result for max average degree. And it's a sort of a similar thing for each choice of K, for each row K. Right, so if you have this, then your potential is always non-negative, and then by the theorem, you can't contain a critical subgraph, and so you'll have the coloring that you want. So what are we going to do? What we really want to do to facilitate the proof by induction, we want to allow pre-coloring. So that means that we're going to say that some vertices are forced to be colored I and some are forced to be colored F. And we're going to go even further, and we're going to allow sort of a richer type of pre-coloring where we say, okay, this one is just colored I. This one, it's U2, which means that it's uncolored, which means it doesn't have a forced color of I or F, but the 2 says that it already has 2 sort of fake neighbors that are colored F. So if it gets colored F, then it will create an F component effectively of order 3, just from him and his neighbors. And if he has other neighbors that get colored F, then the component would be bigger. Here, this is saying that this vertex is pre-colored F, and it has 1 more fake F neighbor. So this here is really just shorthand for this. So the I is the white vertices, the F is the black vertices, right? And so you're saying he's colored black and he has this extra black neighbor. He's not colored white or black yet, but he has these 2 fake neighbors, so that if he gets colored F, then he'll add 3 to the order of his F component rather than just the 1. And I'll say more about this on the next slide, but what we're going to do to simulate this, what we're actually going to do is we'll have gadgets that you hang off of these vertices to force them to be colored F. And so really, this is just some very compact notation for some graph that has these big gadgets hanging off that's going to force any FK coloring to look like this on these vertices. And the reason that we want this compact notation is when we go to pre-color our vertices, we don't want it to increase the order of our graph. We want to be able to invoke the induction hypothesis and say this graph, I took some subgraph and then I pre-colored it and then I was able to invoke induction. And I don't want the order of my subgraph to grow when I do the pre-coloring. All right, so if I'm going to have this sort of very rich idea of pre-coloring, then I need to generalize this potential function, right? And so I'll say more about where these coefficients come from in a bit, but the intuition for now is just that vertices that have lots of F neighbors, they don't give you very much freedom. And so since they don't give you very much freedom, they shouldn't really count very much towards increasing your potential, right? You don't have very many choices. If you have an uncolored vertex, it's giving you 15, which is a lot. But if you have a vertex that's sort of colored F and it already has an F neighbor, then that's only going to give you 5 towards this potential, right? Because it doesn't give you as much flexibility. And where do these coefficients come from? Like I said, I'll get to that on the next slide, but the point is they're going to come from these gadgets that we're hanging off. You're going to do some computation of the potential using the gadget, and then that's going to tell you what these coefficients really should be. Okay, so now if I'm going to prove it with this more general potential function and prove the statement for these pre-colored graphs, then I need to enlarge my definition of IFK critical to apply to pre-colored graphs as well. And so it's sort of the same thing as before. You don't have an IFK coloring, but every subgraph does. And further, every weakening of the pre-coloring does as well. And so what that means is, that means if I take this F2 and I were to erase it, so this is uncolored, or even if I were to change it to an F1, right? Then that's sort of a weaker pre-coloring, and so now I'm going to have an extension of that pre-coloring. And you can think about what's really going to be going on is you're going to say when you expand this whole thing out to put all the gadgets on, that graph is going to be critical. And so if you remove any edge, that's going to make the sort of pre-coloring here, it's going to be weakened in some way. All right. So let's state the real main theorem now is sort of what we said before, but it's for pre-colored graphs, right? If G is a pre-colored graph that sort of allows I, and you can have U0, U1, U2, U3, U4, and F1, F2, F3, F4, then if you have an IF4 critical graph, then its potential is at most -3, same as before. So just to make this concrete, this graph here is, or let me say this graph here, is an IF4 critical graph. So if you look at it right now, we don't have much choice about how to color things. There's only this one vertex that's uncolored. And if you color it I, then that's a problem because I is not an independent set. And if you color it F, that's a problem because you get an F component of order 5, which is not allowed in this IF4 coloring. So this doesn't have an IF4 coloring, but if you delete any edge of this graph here, or if you uncolor any vertex in this graph here, then you do have an IF4 coloring of that. And so that's what's verifying that this graph here is IF4 critical. And so now if you go through the computation, what's the potential of this graph? Well, I gives you potential 4. So this is telling you, this is the number of vertices that are pre-colored I. And U2 is going to give you potential 9. This is the number of vertices, in this case, just 1. So it's 4 times 1 plus 9 times 1 plus F2 is giving you the 5. So altogether you get 18 minus 22, which is -4. And that's good because -4 is no larger than -3. So this is not a counterexample to this theorem. Okay. So let me just pause and ask if there's any questions. Nope. All right. So let me, what I want to tell you next is a little bit about where these coefficients come from. And the idea, as I mentioned, is we are going to simulate those pre-colorings with gadgets. And so if you have a vertex that is presently pre-colored UJ, so you can think, for example, just a normal uncolored vertex is colored U0. And if you want to force it into the set U1, where you have one pre-colored F neighbor, then you hang a pendant triangle off of it. And the idea is that always at least one of these guys is going to be colored F, right? And so if this guy gets colored F, then he'll pick up at least one F neighbor. And that works for moving UJ to UJ plus 1 and moving FJ to FJ plus 1. There's one instance where we won't actually do it this way for FJ to FJ plus 1. Occasionally, it's going to be more efficient to simulate it another way. So here what we're doing is you're moving U0 all the way. So this is like roughly FK over 2. You're taking a big jump, and in doing that, you can sort of save a little bit in the cost. And so what this is this should look familiar because this was the left end of our sharpness example, right? This was V0, and this was W0, and this was X0, right? And now if we were to just hang a few more triangles off of this little bit here, we would force him to be in an F component of order K. So if you have a vertex that you want to force it to be colored I, the way to do it is to give it a neighbor that's already forced to be colored FK. And then he can't be colored F, so he'll be colored I. And if you have a vertex that you want to be colored F1, the way to do that is to give him a neighbor that's colored I. So if we wanted this vertex here to be colored F1, we would make up a new vertex that would be colored I. And the way we would do that is we would hang a neighbor of it that's pre-colored FK. And the way we would do that was we would hang this big gadget off of that one, and then a bunch of triangles as well to force him to be in this FK component. And then he's in this, this I, and then because he's I, then he'll be F1. All right. So, right. Oh, so let me just say briefly, then what you do to get all those coefficients that we saw here, what you do is you just take the potential of those gadgets. And if you use more than one gadget, you just sort of daisy chain all the gadgets together that you used in the construction. And that's going to give you the potential. And that's where all of these coefficients come from. So it's sort of interesting to point out that the statement for these pre-colored graphs with this very sort of rich notion of pre-coloring is actually just logically equivalent to the statement for uncolored graphs. Because what you're doing is when you say something about a pre-colored graph, what you're actually doing is you're expanding it out to some completely uncolored graph with these gadgets hanging off. And as I mentioned briefly, the reason that we want the pre-coloring is when we go to do the induction hypothesis, when you do induction, you can use any partial order that you want, right? Just as long as you essentially bottom out eventually. And so what we're doing is we're saying in essence that hanging gadgets off to enforce a pre-coloring doesn't count toward the order of the graph, right? And so then we can take any subgraph, which will be strictly smaller order, we can hang gadgets off any way we like, and it won't make the graph bigger. And so we can still invoke the induction hypothesis. So really the whole point of the pre-coloring is that it allows us to specify our partial order for our induction hypothesis. Okay. So then last of all, why is the potential method better than maximum average degree? So all of these, I mentioned some papers in the introduction where people had done things in this direction, and most of them were using max average degree. And the reason that we're able to get stronger results is because we're using this potential function. And what the potential function does is it allows us this really powerful gap lemma. And I won't get into the proof of this, but what it says is when you take the subgraph induced by any proper subset of the vertices, the potential is actually pretty big. It's something that grows linearly in K. And so what this means is, it means that before we invoke the induction hypothesis, we can sort of mess with our graph. We can change it somehow. And when we make a small modification to the graph, it changes the potential function a little bit. It changes the potential function in a measurable way. And so if you're bounded far away from -3, which is when you can get to be a critical graph, say this was 10 or something, then you can make lots of modifications. You can add edges, or you can identify vertices, or you can pre-color vertices in some way. And then you can argue that all of those things, they're still not going to allow any subgraph of the graph you're trying to color by induction to be a critical subgraph. And so, so this gap lemma is really powerful in giving us more strength for our reducibility. So I haven't talked too much about what the proof is actually doing, but it's a reducibility and discharging proof under the hood. And so what you're doing is when you go to invoke the induction hypothesis, you say, if such and such a thing were in my graph, then I could rip it out. I modify the graph a little bit, and then I pre-color it by induction. And then I go to extend it to the whole graph. And that modification that I made before I pre-colored it, before I colored by induction, that modification gives me more power for my reducibility. Now, sort of the bad case that I couldn't handle before doesn't happen because I put in an edge or something in my modification before I invoke the induction hypothesis. And so it gives us a lot more power for the reducibility, and then we finish everything up with discharging, just like is sort of the standard approach for these types of proofs. Okay, so I sort of said a lot. Let me recap and just tell you what we did today. The main problem was we want these IFK colorings, which what they are is they're a partition of V of G into an independent set and a set that induces a small forest where each tree is small. Each tree has at most K vertices. And so here's an example that we talked about. This is an IF6 coloring because the orders of the trees are not more than 6, and the white color class is really independent. So what we did, the main theorem gives sufficient conditions for having one of these things in terms of the max average degree. And I showed you some sharpness examples. I just showed you sort of the case where there's 3 of those triangle chunks, but you can build as many triangle chunks as you want. So that's an infinite family of sharpness examples for every K. And I mentioned this in passing, even if we drop the requirement that FK be acyclic, if you just say that each component has order K, the sharpness example still goes through. It didn't actually use the acyclic requirement. So this partially answers this question of Henry, Norton, and Wood, and improves on a bunch of previous results. And one of the big things that allowed us to do this was using the potential method, because it gives us more power for the reducibility. We also generalized to these pre-colorings, sort of a very rich notion of pre-coloring, and that made it, I think it makes it easier to understand when you're doing the reducibility. It gives you a lot of things that you can invoke the induction hypothesis on. And the gadgets tell us the coefficients in rho. So when we generalize, we have to come up with the coefficients for each of these pre-colored vertices. And the way we do that is we just compute the potential for the gadget that's simulating that pre-coloring. The gap lemma, I didn't go into this very much today, but what makes the potential method really powerful is that you get this gap lemma, which says, in essence, that you can modify your subgraph before you color it by the induction hypothesis. And that's really useful because you can sort of think of when you're trying to do reducibility and there's sort of one bad case that you can't handle in your attempt at a reducibility proof, you put in some modification to your graph so that that bad case can't happen. And so you're able to prove that a lot more things are reducible. And then we finish with discharging. And the paper is on the archive here if you're interested. So let me stop there. Thanks.
Thank you, Dan. Are there any questions?
So in the gap lemma, do you use some sort of quotient, like in the normal potential method?
Yes, yes. So if you, I could explain a little bit of what the gap lemma looks like. It would take, 5 to 10 minutes. So I'll hold on that. But if you want, after I get done with the talk, I'll be happy to say a little bit more about that. But it's very much, you sort of, you pre-color something, you contract, and it's essentially just the same proof as the proof of the potential method in other papers.
Yeah. So it's a homomorphism then? Just like
yeah, I suppose so. Yeah.
Are there any more questions?
I was wondering what like the bounds are for the Hendry Norton Wood question. I remember them mentioning some general conjectures in this direction that aren't, of course, tight like this. But
right. So I believe that their conjecture is that their question was, I don't know if it was a conjecture or a question, but it was, is G of AB, which means you want one subgraph to have mad strictly less than A and the other one strictly less than little a and strictly less than little b. I think the question was, is it always true that that bound is at least A plus B? And I think that the one place that you get sharpness examples for that is from the cliques.
Is that for A and B being integers?
Yeah, I think it's true when A and B are integers. If you take a really simple example of just K3, right? So the mat of K3 is 2, and you can't partition it into 2 pieces where each side has mad less than 1, because you get an edge in one or the other. And that works in general. I took A and B both to be 1, but the same construction, if you take the clique on probably A plus B plus 1 vertices or something.
Great, thanks.
Yeah.
Are there any more questions? Does this have any relationship with the defective coloring Hardwiger type results that have been coming out recently?
So, I mean, it certainly is some variation on defective coloring, right? Or maybe sort of an imbalanced clustered coloring, I think might be a better. So clustered coloring, what they want is that each component of your monochromatic subgraphs has bounded order. And so this definitely fits into the realm where you have 2 colors and one of them has order 1, and then you have order something for the other one. Mm-hmm. I don't know more about it than that, I guess. I think I'm trying to think if I haven't seen anything that uses similar techniques to this in their papers. So.
All right, thank you. Are there any more questions?
So what happens if you do you think all the sharpness examples have lots of triangles?
Yeah, so that's an interesting question. I do. I think it would be interesting to say, what if you require girth at least 4 or something like that, or triangle free. I think that the potential method, sort of the version that I used here, kind of breaks down because when you go to,
Why can't you just do what like Luke does in some of his papers and just attach on a negative number of triangles function,
yeah,
and then you'd still have the
I
same.
think that would be an interesting thing to look at. Sort of everywhere throughout this paper, when you're using gadgets, all of your gadgets have tons of triangles. So I think it would require somewhat of an overhaul if you were going to try and adapt these methods.
But I mean, it's not clear that having a gadget having a triangle is bad. You would prove a stronger statement about all IF critical graphs, but you change your potential function to count triangles as well.
Sure. Yeah, it's possible. It's not something that I've thought about a lot. I'm familiar with one paper where Luke did that. I haven't thought about it much in the context of this question.
Are there any more questions? If not, then thank you, Dan.
Yeah,